This presentation is going to look at some advanced digital forensics, and the focus will be on how we can use open source digital forensics frameworks. So we'll have a quick look at what a disk format actually looks like, and then we'll go on to use the SleuthKit digital forensics framework. So the tools that we're going to be using are the SleuthKit. So we'll demonstrate it in both Windows and also in Linux, but in terms of the Windows version, you can download it here, download it from there, and then what you should get is a whole lot of executables, such as here. Okay, so we're going to use some of these commands to be able to process our disk images. You can also download the Linux version and it should work in the same way. The other tool that we're going to use in the presentation is to be able to mount our raw disk, and I've just used the OSF mount package to be able to do that. Okay, so we're going to try and learn some theory behind disk formats and partitions and so on, and then look at how we can use the SleuthKit to be able to analyze our disk systems. So the basic process that we have for our analysis from the beginning to the end is really that we have to prepare our capture, our analysis, the scripts and so on. We need to understand where the data information is and how we could gather it. Often we have a finite time to be able to gather that information, so we need to make sure that we're actually well prepared. After that, we would identify the sources of information that we require and hopefully then acquire it. After that, we might use an open source framework such as SleuthKit to be able to analyze the data. From there, we'll have some sort of reporting, and then we might require the data to be shown sometime in the future, so we would archive it in some secure manner. There are certain guidelines for producing the evidence. One of the key things is that the analysis and the process that we go through shouldn't actually damage any of the data that we actually have. There should also be an audit trail, and whoever is investigating should be competent to do so. Okay, so that's the best practice. As we move to larger and larger disk systems, it becomes more and difficult to do a static analysis, so we'll see some of the methods that could be used for that in other presentations. So normally we gather information from memory that's stored either from traditional hard disks, HDDs, and with this we might have a 3 terabyte SATA drive. It takes over 6 hours to be able to take a complete image. As we'll see, we can have a RAW format, a DD RAW format, and it can take up to 6 hours to actually create that from a 3 terabyte hard disk. The great thing about them though is that they are quite inexpensive, only about $0.04 per gigabyte, but they suffer from basic throughput. It's only about 123 megabytes per second, and the number of operations that can be passed back and forward to the disk is quite low. We typically define that as input-output operations per second. The move though is towards SSD, and SSD is typically available in sizes 128 to 512 gigabytes. And with this, the memory itself is much faster, and it can only take up to about 17 minutes to be able to archive a 512 gigabyte drive. But the cost is much greater, 0.74. We can see it's much greater than the cost of a hard disk. But the throughput is much better, typically ×4 or ×5. And you can see the input-output operations is also vastly greater with the SSD. And in between we have flash memory, So flash memory can vary from just a few megabytes per second to the newer formats. The HS2 goes up to 312 megabytes per second, and standard ones give about 25 megabytes per second. And again, it costs about the same as an SSD type drive. So there is often a balance to the type of storage that's actually used, but the SSD and flash are obviously the way that many systems are actually going now. So more and more we actually see the data captured from these types of devices, such as from mobile phones, flash drives, SSDs on laptops, and so on. So we have many devices that have some sort of storage on them: a camera, a USB stick, laptop, iPad, mobile phone, PlayStation, and so on. All store either on static or traditional hard disks drives. As I said, a static drive can take up to 11 hours, where for our SSD it takes just maybe tens of minutes to be able to collect it. So what we do to make sure that we can then use the device again and we can archive it is that we normally use a package such as DD, FTK or Encase to be able to capture a copy of the disk. We can then use this and we're not destroying the original disk. So we use a read-only blocker. We have a write blocker which will do a read-only from the disk to produce the output. Obviously these files are large, so we need to make sure that we can actually store them in some sort of way. The two main methods that we have for this is to do a bit-by-bit copy, and that's with DD, and that produces a raw format. That tends to be very large, and we have no metadata in there at all. Or we have the metadata formats of an Encase evidence file or an advanced forensics format, or AFF. So these will then be used to be able to be fed into some sort of open source forensics analysis system such as SleuthKit. So there are many digital corpora images around that it's possible to train on and look for evidence. Okay, so the methods that we have is, once we've collected our data, such as from our DD application, to create the raw file, we would then use a package such as SleuthKit to be able to analyze it. So the basic process that we go about is we would typically store it to some sort of database, SQL, MySQL. And then with this, we would then look at the file analysis phase. With this, we're creating our MD5 SHA-1 hash signatures to make sure that there are no changes in files and so on. We might do a hash lookup for certain known hash signatures inside our files, and then identify each file with their magic number. Because normally a file has a magic number at the start of the file which will identify it, and even if it's embedded within other files, we can still see this magic number appearing. We might do some zip extract if files are contained within zip files, and add any text that we've gained from our file analysis to the keywords that might be used inside the analysis later on for our post-processing phase. Okay, so a lot of this does the preparation for the next phase, which is post-processing. And with this, we might look at the registry. We might use a reg ripper to be able to look at the keys that are in the registry, some web browser analysis. Then for some keywords, we would do some keyword search. We typically look through the whole of the disk for certain content types, text searches, email addresses, passwords, and so on. And then check for some well-known files and folder names, and then eventually create some sort of summary report. Okay, so this is often the procedure that we'd go through to be able to create our system. All along, we're saving to our database to be able to create the evidence and create the case notes. So let's look a little bit more closely at the disk format. With this, what we want to do is to be able to understand how the data is actually laid out from a binary point of view. Okay, so you should find there is an associated web page here, and if you're interested, here are all the different file types that we can look at in terms of the magic number, but in this case we're interested in this raw format. So this page should show you what the binary format is of an image. In this case we're going to use a raw image taken from a Canon camera. It has some deleted images on it, and we'll see if we're able to undelete those images. Okay, so the first thing that we should say about the raw format that we get is that the magic number is actually here. So in most of the other systems, the file systems we've looked at, the magic number has been at the start of our first segment. Okay, this is a 512 byte segment. That's typically how we segment the disk up. But this is in the first segment, the first sector. We have the second sector here, and so on. So the page should show you each of the sectors as they are defined. Okay, but at the end of the first sector we see this magic number 55AA. So you should always see that in terms of the file that you're actually looking at. Okay, so this is a real image, a real DD image, and you can capture them from the digital corpora systems online. Okay, so let's look at the basic format. You'll see there's lots of zeros in this file, but it's really the first sector that we really want to look at, and will give us the information. So the reason it isn't a magic number is that the first part of the master boot record is actually our executable code, and it's this code that will get the system booted up and started and make sure that our disk and our disk partitions are actually loaded. Okay, so this shows an example of a DOS disk here. This is the machine code that is actually run from the first byte of the first sector, and what it is really is machine code that we see. So let's see there. So there's the FA. So FA is clear maskable interrupts. We have 33C0, and there we go. So this shows us our machine code that we actually get. And if you view another lecture, we'll be able to look in more detail at the opcodes and the machine code. But you can see there is the standard format of the code that's actually run. So typically different operating systems will have their own type of code that's actually run there. But normally there is a standard sign of this, and we've identified this on the page here. That we've identified a master boot record DOS there, and there's the magic number there. We've also found that. Okay, so that's a key part. This is our DD file that we're reading in, our raw file, and this is the format that we get. The next part of it identifies the error message that we get if it's used incorrectly. This is the error message contained inside there. There's zeros there that are also included to partition up this message. After this, there's a whole lot of zeros that happen, but then what we get at the end is the start of our partitions here. So in this case, there are 4 partitions defined on potential for this system. So we have 16 bytes reserved, 16 bytes from here to here. All of this is our partition there. And then the next 16 bytes will identify the next partition, and so on. So we go down to there, that's the next one, goes up to there, and then the last one is there. You can see that there is no extra additional partition information with inside there apart from this first one. So the way that we read the next part is that the first byte 00 identifies if this is a bootable partition or non-bootable. In this case, we're using a flash drive from a camera, so it's non-bootable. But obviously, if it was XP or Windows 7, we would have a bootable partition. So we'd see 80 there or 00. So there's a whole lot of other things that will actually define where the data is actually going to begin. So in this case, we're starting in sector 1. So that means that the data that's going to follow this sector is actually the start of it. The next important one is here. The 04 identifies the system type. It could be FAT16, FAT32, and so on. So this is an important indicator for the actual file type. After this, we see the end sector of our data, because our data is laid out inside these sectors. And then what we have is the number of sectors inside the partition, and we'll see that a little bit later. In this case, there's 40,749 in there. Remember that this is Little Endian format. Little Endian defines that we read this way. So this data from the least significant byte is ED4D. And when we do the hexadecimal conversion, we end up with this value, 60,749. Okay, so this is important information. Obviously, if this gets corrupted, then our whole system could get corrupted. At one time, we used to get viruses planting themselves in here, which meant that an intruder could get access to anything because they would actually boot the system up from here. Again, if a system is able to get into this part here, then they can do a lot of damage inside the partitions. Okay, so we're going to use the sleuth kit to be able to analyze an image. So we use the same images we've done before. It's a raw file. The format is defined here. Okay, so as we said, the first part of it is gives us our executable code, then we have the message, and then we have the partition information here. So this is the type of data that's read by our system to be able to understand it. Okay, so let's have a look at, let's see if we can mount the drive. Okay, so with this we can go and we can find our drive. So in this case, what we're looking for is raw file format. Here we are here. Okay, so we can load the entire image, but we'll just look at one partition to load. Okay, so we're going to mount it as the J drive. There we go. Okay, so there are some images there. So that's the disk that we're going to analyze. So what we're going to try and do is we're going to try and carve out those images. We're going to have a look to see what's happened on the disk. But this is our DD file here. Okay, so what we'll do is we'll just unmount that. So what we'll find is that with these tools we can actually carve out any files, even if they've been deleted. Okay, so the first program that we'll look at, or the first analysis package that we'll actually look at, is for this one, which is the MMLS. So mmls is a good first package for us to be able to run, because it will actually show us where the partitions are and so on. Okay, so if we go and have a look at this, so I've set up just some simple commands here, and then we'll just bring it over here. Okay, so our raw file that we have is this one here. So it's the images taken from the Canon camera, and what I'll do is I'll just paste that in. Oops, we'll just paste it. Okay, so that's telling us that there's a FAT16 partition. There's the 04 that we've seen before, and it starts at 51. Okay, so that's an important point that we need to understand. We need to define. That's the sector number that we're going to look to be able to get the start of our disk images in this case. So when we looked at our disk partition, this was non-bootable. Okay, and then we identified that the 04 here was actually to do with the FAT16. Okay, so that it's there. There's the 04. And then over here we have, for this part here, this bit here, that's the number of sectors within inside the partition, which is 60,769, which is exactly what we have then. And then we have 51 preceding sectors before we get to this one, and there it is there. So this part here is the part that's really been identified as part of this mmls. We define the file system, in this case with the -t. So when we look at if we want to look at the different types that are supported, okay, so in this case we can choose from DOS, Mac, BSD, Sun, or GPT. Okay, so if ever you're stuck and don't know what one of the options are, use the -t list in this case, and we'll get the type of partition. Okay, so now armed with this 51 is a key value for us now, because that's where we're going to find the first partition that we're going to look at. So the next thing we can do is that we can work out the inode information. And inode gives us the basic file information, not the file contents, but each file will be identified with an inode. So in this case, we can take our offset, and we've identified now that it's FAT16. Okay, so with this information we can now populate this. It's a raw format, so let's have a look at this command in a bit more detail. Okay, so ILS, so our offset is 51 sectors, and we can then do that, and that will show us all the different file systems that we have. Okay, so we have our partition and we have our file system. In this case, what we're going to use is FAT16 there. So that's FAT16 is what we've used there. And the next thing is our format for our disk. In this case, what we've got is a raw format that we're going to be using. There's the raw format there, but it can also be other formats that we could take directly from our disk, NTFS and so on. Okay, so we're going to use that, and then we're going to specify our DD dump. Okay, so let's do that. Let's try that one and just see what we get. And this is going to give us our inodes this will be used to be able to find out all the files on the system, the location, and so on. Okay. So the next package that we can use is the FLS, and FLS will give us all the files or folders or one or the other, and it can give us deleted files and so on. So we can see here when we use it, we're just using the same things again, this raw, and then the -R option. Let's have a look to see the different options that we can have for that. Okay, so the -R option will go through all the directories and have a look. Or we could display only files if we want, or we could display only directories. We can display only deleted entries and so on. So this one is a really clever little package that will allow us to be able to find the complete contents of the disk. So in this case, we're going to go through all the folders. So as we've seen when we mounted the image, there is a Canon DC file, and then there's a DSIM, and then there's a 100 Canon folder beneath that, and then there's a whole lot of files that we can actually see. Just truncated this output here. So what we'll do is we'll have a look at this little program, and clever little program it is. There we go. So that's identifying all the images. If any had been deleted, we'd actually see the first character actually missing from the file, because that's what happens in the file allocation table. We lose the first character, but in this case it doesn't look as if these are deleted at all. And there are various other files on the system. Okay, so that's useful. So we'll be using this information later on, so that will tell us all the files that we've got on the system. But then what we can do is that we can output to what's called the body file text. And in this case, we will be able to export all the time information, a timeline about the file. We then run a Perl script, mark time, to be able to read this body file and then output a CSV or spreadsheet type file, which will show us the complete timeline of the image. So let's run these two. Okay, so in this case we're going to extract everything from the top level / directory. It's going to go into a text file called body file. We're then going to run this Perl script. So I've installed Perl on my machine, so hopefully when I run the Perl script, it will run Perl. And this is what this is here. Okay, so if I just paste these two files, so I'll do it one at a time, so we can actually see what the format looks like. Okay, so this one will create our body file, paste. Okay, so that's what that looks like. Okay, and then what we can do is that we can then export that as a dump to a CSV file, and this is going to resolve the times back into real times, into markout, and then what we should do is be able to have a look at that. Okay, so this is try to resolve the times, the things that have actually happened on the system. We can see here that some files were deleted. And so on. Okay, and it should give us the time there too, size of the file, and the writes on the system. Okay, so with this file we can get a timeline of what actually happened on the disk. we can obviously take it between certain time limits and so on. So the next thing we'll do is we'll extract a file from the disk. So if we look back at our inodes, okay, so at inode 1029 we had image 1. Okay, let's extract image 2, which is at 1030. Okay, so we're going to use the icat. icat will extract the file information at that inode. So icat, and we'll take it from 1030. And we'll put it into there. Okay, so icat will look 50 of an offset, start the partition from there, then read the file, and when we come to inode 1030, should find that image. That inode contains all the information required to extract the image, and hopefully we have an image. Okay, so these are test images. Each one you should get a different number on there. Okay, so a clever little program there. We can extract any of the file contents, even if they've been deleted on the system. In fact, we can see a deleted file inside this one here. Which is another test file. Oops. Okay, so look, we've lost the first character, and what's happening there is that this file has been deleted. We can see there that it has a little star, so we could actually try to undelete that, hopefully, if we can use our icat there. Let's check the file name. That's right. Paste. So this time the offset is 97, so I'll show that in a little minute. So in this case, we are at here. And let's see if we can extract that one. Okay, so just check icat 97, and that's the file. We got the wrong one here. So this should be 1029. Goes into there. Okay. And there we go. So there's the file that's been deleted, and we've managed to extract it. So we lose one character from the file when we delete it on the file system, but we can see here we can easily bring it back again, even though it's been deleted. And so I'll just show you why I used 97 for this disk image. This is a different disk image. Okay, so there's 97 there. So that's why I use 97. And if you're interested in the file contents, there. Okay, so that's shown a good example really of how we can extract even deleted files. Let's actually have a look to see if we can actually load that one onto our system. So this was this one here. Just load the DOS partition. Okay, so there you go. So we extracted, you can see here it's only shown this 0126 but what we managed to do was to undelete this file here, image 125. Okay, so even though you delete files from your phone or from a memory system, there is no guarantee that they've actually gone. Okay, so there are many other packages that we can use. fstat allows us to gain all the information about the drive for the system, the label, and so on. So this will give us more detailed information. It will actually show us where the files are mapped to, because we have fragmented the system. Also shows us where the bad sectors are, and so on. So you might ask, what is this? How does this relate to Linux? Well, we can use the exact same tools inside Linux. So what I have here is a Ubuntu image. So I've downloaded the sleuth kit, and then I've downloaded this corpora, the same raw file that we saw before. So that should be in our downloads folder here. Okay, so there it's there. So what I'm going to do is I'm going to use the same analysis. Let's see where we get to. Okay, so can we copy and paste? There we go. Okay, it's just the exact same format that we have there. So let's go and have a look at the next one. The next one was for our inodes. Let's see if we can use the same command for that one, and we can. Okay, so that works. Then the next thing we did was to export our timeline to our body file. That seems to work well. And then from here, let's see if we have our Mac time, and it's there. Good. So let's do our Mac time here. Mac time. Let's paste it in. So unfortunately we don't actually have a spreadsheet installed on here just now, but we'll have a little look at the file. Okay, it just looks like a standard file, and it's similar to the file that we actually saw inside the Windows version. Okay, so if we had a spreadsheet installed, then that would show. And then what we want to do is we want to extract our file from there. So let's try that. Okay, let's see if we can, our file is there. Okay, and then the last one that we would do, we can do what's called a bulk extract. So with the bulk extract, what we can do is we can actually export the whole of the image, and then we could search through that for certain strings. Okay, so let's have a look at that. So that's what our image actually looks like when we extract it. So we could search for certain strings inside there if we wanted, such as using the grep command. Okay, so you can see there that this is same programs are actually used to be able to get the same types of analysis. Okay. So let's go back to our presentation. Okay, so in this presentation we've really looked at the outline of a disk format. We looked at the master boot record and how we can analyse that, and then how disks are actually structured with partitions. Now we can look at the hexadecimal format and understand that, and then how we can use an open source tool such as the SleuthKit framework to be able to analyse our images.